That you are muted.
Thank you. So in the last class, we have discussed CNT based MOSFET or CNT based FET rather, and we have started graphene. We will briefly cover graphene today before we move to discuss characterization equipment for nanomaterial. Uh, so this Uh, just let me briefly mention again. So CNT based MOSFET or CNT based FET of different type. The easiest one is backgated CNT, where the gate is from the bottom or from the back. Okay, and you see this silicon layer has to be thinner and has to be highly doped, so that you have to apply lower voltage from the back side. Still the voltage is pretty high, maybe tens of volt, because usually silicon substrate is several hundreds of micrometer thick. And here graphene acts as a channel. This is your source and drain. This is not conventional FET, because your conventional FET you have like you form channel, but the channel is there, and you can apply appropriate voltage from the gate side and from between source and drain uh, to achieve conduction through this channel. And there can be a single carbon nanotube or a bunch of nanotubes depending on how you are making it. This is the simplest way of realizing CNT based FET. And then we talked about top gated CNT FET, where we put CNT on the substrate like the one before, but here the process is a bit complicated, because then you deposit oxide. Okay, gate oxide of many kind. You can use SiO2 or you can use other oxide if you want, and then on top of that you put your metal layer, so that will give you gate contact. And then there is source and drain. So this is a little bit complex technique rather than the backgated CNT FET, but this structure is like conventional FET structure, and you have to apply much smaller or much lower voltage from the gate side, because you can see that here gate oxide is much thinner. Okay, compared to the backgated CNT FET. Then we have talked about wrap around gate CNT FET, where gate is wrap around the CNT. Okay, and this will give you better control, but you see the process of making this or fabricating this is much more complicated. After realizing this gate oxide around the CNT, you etch out the gate oxide from the source and drain region, and then you deposit contacts. You can also dope CNT if you need. Okay, at the source and drain region. And lastly, we have talked about suspended CNT FET, where we have like CNT suspended on source and drain, and it is directly not in contact with the substrate. People have seen that this kind of structure will give you much higher mobility than the conventional CNT FETs, because the carbon nanotube is not in contact with the substrate. But obviously this is the most complex technique to, structure to fabricate. So these are the things we have discussed, and we have then mentioned that CNT shows ambipolar behavior, because the way it works, it can be a p-type FET, or the same CNT FET can be an n-type FET. Okay, so both the FET behavior you can see. So this is why it is called ambipolar behavior or ambipolar FET. And then we mentioned that CNT FET can work as the working principle. The popular belief is CNT FET acts as a acts because of thinning of Schottky barrier. There are Schottky barrier exists both at the source side and the drain side, and you apply gate voltage, okay, to thin down the Schottky barrier. and depending on which barrier you are thinning, you might have the whole conduction through this valence band, or you might have the electron conduction through this conduction band. Okay, so this is how it will give you both p type and n type conduction, and it can access a both p type or n type FET depending on what kind of voltage you are applying at the gate, and also between drain and source. Then after mentioning that, we have started talking about graphene. So graphene is a kind of wonder material. It is like one atom thick. It is one atom thick only. Okay, so if from the graphite, which is like a stack of layers connected through van der Waals force, if you manage to detach and achieve a single layer, then it is like a then it is graphene. Okay, so monolayer of carbon. Monolayer means single layer of carbon or graphite, right? So graphene is a 2D network of sp2 bonded carbon atoms arranged in a honeycomb structure, and it was first demonstrated by Andrei Guillaume and Novoselov in for that I think beginning of 2000. From they are from University of Manchester. They have done it through mechanical exfoliation. You remember we were looking at a video in the last class where the video was from Manchester University itself, where they have demonstrated how they have achieved carbon graphene for the first time. The graphene has a lot of unique properties. It is a zero band gap material. Okay, so it is a zero band gap material. So it is called semi metal. So in case of metal, you have like conduction band and valence band, there is overlap, but in graphene they are not overlapped, they are touching at a point. Okay, and the band gap is zero. So it has remarkably high mobility because it is, you see, it is a single layer material. Okay, so it has remarkably high mobility. Okay, the carriers can zip through the material, almost ballistic transport you can achieve. And it has very good mechanical properties because it is sp2 hybridized material, and there are different ways to make graphene. One of the technique is mechanical exfoliation technique. That technique we have discussed, or we have shown in that video. There are other synthesis technique also, like chemical exfoliation, chemical vapor deposition, and so on and so forth. So I'll briefly cover those techniques. Let me go to this file. So this is, you have seen before. So a single layer, if we can detach from this uh, from this uh, graphite sheet, okay, then you will get graphene. Okay, so these are graphite, these are layer by layer stacked together, is known as graphite. So if we can detach one of these layer, then it is basically graphene. You see, this kind of structure is known as honeycomb structure, and there are carbons at each corner. Right now the thing is, uh, it has various application. Graphene, apart from graphene based FET, we can apply graphene for various application, like graphene can be used as sensors, can be used to make displays, and so on and so forth. Various other devices, for example solar cell and all that. So it has huge amount of application, and people have been looking at it and try to modify it to achieve different applications. Now there are different ways to make graphene. As I told you before, one of the very one of the easiest technique, and this is the technique first time developed in University of Manchester, is known as mechanical exfoliation technique. Okay, in mechanical exfoliation method, if you remember the video, you start with a silicon wafer, or on top of silicon you will have like SiO2, because SiO2 acts as an insulating layer. So you start with a SiO2 wafer. On top of that, I mean, you will use this later, but what you basically do, you use a scotch tape. Scotch tape is like a tape which is very sticky, and you have a very highly ordered pyrolytic graphite. Okay, highly ordered pyrolytic graphite, or known as HOPG. You use this to put this on the scotch tape, firmly press it, and then you remove the scotch tape. You use the tape several times, so that in a new place of the scotch tape, you stick it to a different place of scotch tape in a new place, remove it, and again put it in a new place, and then remove it, and so on and so forth. Every time you remove the scotch tape, you are basically detaching some of the layers. Okay, and this is how you basically end up with a few layers of graphene. And then what you do, you put that scotch tape on the wafer or on the substrate, which has like SiO2 substrate, and then you carefully remove your scotch tape, so that the few layers of graphene or single layer of graphene is then transferred to the SiO2 wafer. Okay, this SiO2 is important because it is found that if SiO2 is around 300 nanometer thick, then the layers can be seen in the optical microscope. Usually layers are very thin, but the way if you use like SiO2 around 300 nanometer, then it is possible to see graphene, a purplish color, in the optical microscope itself. That was at the end of the video, that was showing by a person in Manchester, right? So this is in a nutshell is the method, which is very simple as well as very crude. Okay, but they achieve graphene by this particular technique, and they means Andre Gume and Novoselov performed several important experiments with it, okay, to find out characteristics, to how to make devices and all that. For that they got Nobel Prize in 2010. Now, so apart from this is known as mechanical exfoliation technique. There are other technique also. I think you clearly understand this particular technique is not for a high yield. Okay, this is to achieve the graphene so in the laboratory scale, so that you can study its performance for various applications, but it is not a technique for high yield, obviously. Now, so there is one method known as chemical vapor deposition technique. So you remember chemical vapor deposition we did talked about while we are synthesizing or making CNT. Okay, here in this particular method we use copper foil of few tens of nanometer, few tens of micrometer thickness, and we anneal copper foil around 1000 degrees centigrade for an hour. Anneal means we basically the heat treatment. Okay, then we use acetic acid. Okay, the foil is placed inside a CVD chamber, that is chemical vapor deposition chamber. You remember CVD chamber was basically a chamber where you have heater, you have different gases which you can pass through it. Okay, and you can of course maintain pressure and all that. In this particular case of making graphene, you have to use methane, CH4 and H2 gas flowed inside in the ratio of 1:4 at a temperature 1000 degrees centigrade for around 5 to 10 minutes. The substrate with graphene film is allowed to cool down to room temperature and inside the chamber. So you can then detach that graphene film which is grown on copper foil from the copper foil. There are ways to do that. So this is in a nutshell is a chemical vapor deposition method for realizing graphene. Similarly, so I have mentioned the papers name. You can go through if you want to know more about it. Uh, Here also, I mean, also you can see lots of if you want to see this particular method. Okay, there are lots of papers published from University of Manchester at the beginning of 2000. So you can see them from the group of Manchester, Andre Guillaume and Novoselov's group. There are lots of papers are there. And then there are another technique which is known as thermal reduction of graphene oxide to realize graphene. So graphene oxide is not graphene. Graphene oxide is basically oxide form of graphene. So again, what you can do in people a very popular method is modified Hammers method so this is a chemical technique of realizing graphene. So in modified Hammers method, you basically first fabricate or make graphene oxide. Okay, and this graphene oxide then so this graphene oxide contains not only, I mean, it contains that honeycomb like structure, but it contains several functional group. Okay, for example, COOH, CO, these kind of functional groups are there along with those honeycomb structure. So it is basically a oxide of graphene. So what people do, people then reduce this graphene oxide to realize graphene. There are different ways to reduce graphene oxide, and one of the reduction technique is thermal reduction technique. Okay, so you heat treatment this graphene oxide. Okay, and you basically reduce or remove those functional groups to end up with quote unquote graphene, but it is not 100% pure graphene because all the functional group will probably not be removed. Okay, apart from thermal reduction, so let me repeat it once more. This is a completely a separate technique and an unconventional technique. Here you start with a graphene oxide, and the way you make graphene oxide from the charcoal or from that highly pure HOPG, that using modified Hammers method, this is a chemical route, you manage to oxidize charcoal or graphite to graphene oxide. Okay, or GO, usually known as GO. And this graphene oxide, then what you do, you need to reduce it so that you get graphene. Theoretically you can get graphene if you reduce graphene oxide. There are different techniques to reduce graphene oxide. One of the technique is thermal reduction technique. So you use high temperature so that the graphene oxide is reduced to become RGO, that is reduced graphene oxide. Or if you reduce it too much, then it will be technically it should become graphene. But as I said, it is not easy to remove 100% these all these functional groups attached to this honeycomb structure, but you will get a quite good property of graphene out of this. And also this particular technique is like high yield technique, so you can have like quite a lot of graphene out of this process. Also CVD technique is high yield technique. Okay, relatively high yield technique compared to that of the mechanical exfoliation method. In this particular technique you can get but you need high temperature. Okay, and purity is also very high out of this particular technique, whereas this particular method Obviously purity is not very high, although you can get very large yield. The reason purity is not high because you will not be able to remove 100% all the functional groups associated with graphene oxide, right? Now, apart from thermal reduction, there are many other reduction techniques. For example, you can chemically reduce graphene oxide. There are chemicals, okay, for example, hydrogen or NaBH4. This is a chemical reduction technique. In chemical reduction technique, you put this graphene oxide in a sonication bath in a solution, and you apply, for example, here I have written hydrogen, but apart from hydrogen there are other chemical solutions can be used. For example, NaBH4, sodium borohydride, so that can be used for making this for reduction of this geo. Okay. um, there are other techniques also. For example, electrochemical exfoliation. By exfoliation we mean like you are detaching the graphene layer from the graphite stack. We have come across exfoliation in mechanical exfoliation method, right? In mechanical exfoliation we mechanically exfoliate or remove or detach this graphite layer. Here we use electrochemical exfoliation technique, so here it is like a battery structure. You use graphite or HOPG, okay, and you basically separate layers to achieve graphene, right? And so this is a kind of a schematic view of that. So one of the electrode is HOPG and another electrode is PT, as I mentioned, and there is a electrolyte because it is essentially a battery kind of structure, and you apply a bias so that this HOPG or graphite will come in the solution and basically deposit on the PT electrode. So these are different techniques for realizing graphene. Now, as I said, graphene, this is the band structure of graphene. You see, as I said, like its conduction band and valence band touches at a particular point, okay. But these band gap, I mean the band structure you can get only when it is a monolayer of graphene, okay. But you see the graphene, the very astonishing property is it is inert. It is like it can give you very high mobility, okay. So this mobility is very important for realizing electronic devices, okay. um, uh, I mean, people look for making electronic devices from graphene more than that of CNT, simply because the mobility is higher here, even from CNT, and of course from silicon. But the thing is, when you try to realize electron devices, there should be some band gap. But the problem with graphene is, if it is a monolayer graphene, and there is no practically there is no band gap, because the conduction band and valence band touching with each other. So what people do, instead of monolayer, people use several layers. If you use several layers, then graphene started showing some band gap. You can have like uh, you can dope graphene, you can use a strain in the graphene layer to create some band gap, which is important, as I said, to realize electronic devices. Particularly if you go for digital electronics, band gap is very important. So there are ways to achieve band gap, as I said, through doping, through by applying strain, or if you have like, instead of monolayer, if you have like a few layers of graphene, then it opens up its band gap. Okay, now what else? I think that's more or less, this is the last slide of graphene. So graphene also, you can have like back gates graphene fate, or a top gates graphene fate. It should be top gate. It should be top gate. Okay, so this is a backgate graphene FET structure where you have like gate from the back side, but in the top gate you have like that is like more conventional FET and so on. So now here also in graphene, the working principle is same as that of CNT FET. Here also you will get both p type and n type conduction from this FET structure. Having said that, the graphene FET is still in the infancy state now. It is nowhere near to replace silicon, but like that of CNT. But there are different applications and have been coming up where you can use graphene, particularly displays and solar cells and sensors and so on, and it can basically coexist with silicon to achieve or to enhance the performance of your electronic devices. Now this is all about graphene. What I want to show you, there is another video, but again probably you will not be able to hear anything. Can you hear?
No, sir.
You can't hear, so I will not then run this video. This is also in line with how to make graphene and all that. So this is from the University of Cambridge, because they have also very large graphene center along with University of Manchester. But I think this is a similar video where they show that that the uh, that so this is a silicon substrate, and you can use scotch tape to realize mechanical exfoliation of the graphene. Okay, uh, but as it is not uh, not the audio, you can't. So so similar video we have seen in the last class. So you see they have used uh, so several scotch tape uh, to detach graphene layer by layer. Okay, so so you see different parts of it. They are basically sticking and uh, detaching, sticking and detaching, so that you ultimately end up with very few layer. So this is an SiSiO2 substrate, and they put it on this, uh, and then they press it a little bit, and then they bring out uh, the graphene. Okay, so I think I will stop it because it is not audible. Uh, so this is a similar kind of video from University of Cambridge. You see people are wearing this kind of dresses because it is in the clean room. Uh, but when you detach this tape from the silicon from this substrate, you have to be very careful. Otherwise, the layers will be teared apart, uh, and then you can see it under the microscope. Um, so and you can see it under the microscope because there is this SiO2 layer, which will help you to see, particularly because of its reflection property. Um, Anyway, so I'm just stopping it here. Now, so the plan is I'm going to start. I'm going to start um, characterization equipments. I will start with ACM or scanning electron microscope. Scanning electron microscope. So there are various method or technique or equipment available nowadays to characterize nanostructure or nanomaterial. As nanomaterial is not visible under with naked eye, even you can't see it in optical microscope, because in optical microscope you more or less use say say visible light, and in case of in optical microscope, I mean the visible light range is 400 to roughly 400 to 700 nanometer, okay, or visible range. So obviously you will not be able to see nanostructure, okay, using optical microscope. So there are different kinds of microscope available nowadays to see nanostructure. One of the equipment or one of the technique is known as the scanning electron microscope technique. In a scanning electron microscope technique, you will be able to see the structure, okay. And uh, and the apart from scanning electron microscope, there are other methods to characterize your nanostructure. So those methods are not for studying the surface morphology, or not for seeing the nanostructure, but to understand other properties. For example, say elemental analysis you can do. For example, you can find out the crystalline nature of your nanostructure, and so on and so forth, okay. So there are several characterization technique, and we will study some of them in next 2-3 classes. But today let's start with scanning electron microscope. So only this technique we will cover today, okay, and tomorrow we will see some of the other techniques if we can cover. And also next Monday we will next Monday is what, next Monday and Tuesday we will cover some of the techniques, okay. I'm still hoping that we will get a slot 4th or 5th of April, so that we can have a quiz in Moodle, okay. I hope you mark your calendar. So I have already emailed the Moodle team, and let's see which slot we get, and accordingly we have the quiz based on the syllabus we have covered, except whatever we have discussed, except that HEMT and HBT, okay. Now this uh, so let me just open uh, so in short, it is known as SEM, okay. Uh, so this is the one of the most important characterization equipment for your nanostructure, because it will help you to see the nanostructure, okay. Seeing is very important. And so how this equipment looks like. If I draw a very simple schematic view, this equipment looks like there is a, so this equipment is similar to that of e-beam. You remember we talked about electron beam lithography. Okay, so this e-beam machine and this looks little bit similar. So let me draw some small very I mean little bit crude schematic, but the actual machine is much more complicated than what I am drawing now. But this is just to give you some idea how this equipment look like. So there should be an electron gun. Okay, and there should be some anode. Often there might be multiple anodes. Okay, and then there are several lenses. Okay, there are several lenses. These are electromagnetic lenses. You remember we talked about um, we mentioned that we need electromagnetic lenses to focus the electron. We can't use optical lenses obviously because electron is a charged particle, so you need electromagnetic field to control its motion. Okay, so there are several electromagnetic lenses. So it is one of, I mean these lenses are known as condenser lenses. So say how to draw it. Say this is, as is a schematic view. So the lens doesn't look like this. I'm just writing fast condenser lens. Okay, then there is condenser aperture. Okay, what is this aperture we will discuss later on. So there is aperture, it is say condenser aperture. Then there is second condenser lens. As I said, there are series of lenses. Then there is another aperture. Okay, it is known as objective aperture. There is a scan coil. Scan coil. Then there is objective lens. So I have mentioned three lenses: fast condenser lens, second condenser lens, and objective lens. In actual equipment, maybe there is more than that. Okay, and then there is your sample. So this sample contains your nanostructure. All you want to do is want to see those nanostructures. So it is like visual inspection, okay, and verification. So you see, let me just. So your electron beam from here will come out, okay, and this electron beam will be then focused by this fast condenser lens. Okay, sorry, focused by fast condenser lens. Then again it will focus by second condenser lens. Then again with the objective lens, right, and then you focus it on the sample, right. So this is your electron gun, and this is anode, right. So this electron gun can be thermionic type. Okay, so this electron gun it can be thermionic type. What is thermionic? As the name suggests, you apply, you heat up the electron gun. Okay, you heat up the electron gun, and it is basically then managed to emit electrons. Okay, and you use that electron. So you heat up the electron gun, and if the energy is good enough to remove electron, so then electron will come out. Okay, so if the energy is more than that of work function, then the electron will come out, right. So this is thermionic method. There is another method known as field emitted. Field emitted or field emission. Okay, so it will also produce a stream of monochromatic electrons. Okay, field emitted technique is nowadays used in more and more SEM compared to thermionic emission, because it is found that field emission, if we use field emitted electron, then the gun's lifetime will increase. Okay, in field emission you don't apply any temperature. What you do, you apply high electric field, and these guns are very tiny. So you see, if I have a very very sharp tip, okay, and if you apply voltage, say I'm just making a schematic drawing. If I apply voltage between the between this electron gun and this anode, then what will happen is there will be high, the electric field at this peak, okay, of this gun will be very high, and that electric field might be good enough to to bring out electron. Okay, so in field emitted or field emission type of electron gun, you apply high electric field rather than high temperature. Okay, and people found that this particular method is useful for improving the lifetime of the gun. Okay, otherwise you have to change gun very frequently, which is a very cumbersome process. So to avoid that, people move from thermionic emission gun to field emitted electron gun. Now so there are various ways to then use these electrons or electron beam to focused through different lenses. Now it will go through first condenser lens. Okay, so these lenses are electromagnetic lenses. Let me see if I can. I have an image of that which I can draw. Just let me see my note if there is any. No, I'm not finding any image associated with. Yeah, so these. So let me mention these electron guns are either maybe made of W, that is the tungsten, or lanthanum hexaboride. These are popular material to develop the gun. Okay, so you pass, one of the technique is you pass current to heat up the filament, and because of this joule heating, as I mentioned, provides enough energy for the electron to escape. Or you can apply high electric field to extract electron from the tip of the electron gun. Okay, so there can be one anode or several anode. Okay, and so maybe one anode will extract electrons, and the second anode may be used for accelerating those electrons. Okay, let me go to another slide. So there might be several anodes. Okay, so let me see again if I have any drawing associated with that. Also, these can be little bit. There might be many other kinds of arrangements. So let me draw one. So these electron gun might have, as I said, might have multiple anodes. Okay. Anode 1, anode 2, and so on. So these may be used for extracting electrons. Okay, so you apply voltage between this anode and the electron gun, and there might be other anodes. For example, this can be used for accelerating electrons. Okay, in many cases people often use walnut electrode. It is known as walnut electrode. In walnut electrode, that is an additional electrode between the electron gun and the anode. Okay, let me try to draw that. So this walnut electrode is, you see these anodes will have hole in the middle so that the electron can pass through. Okay, otherwise it will basically all the electrons will be will then take the anode itself, right? So that's not the purpose. So you should have hole so that electron can pass through the hole. Okay, now as I said, like there can be additional electrodes between anode and your electron gun. This is known as walnut electrode. Okay, so you will have this kind of electrode between anode and the electron gun. This walnut electrode, what it does, it basically uh, focuses those electron which is coming out from the tip. So the electrons will, so you give intentionally negative bias, okay, so that it pushes the electron inside, and then so this is basically a crossover point, you see. Okay, so crossover point, and this is known as uh, Wenelt electrode, and this is maybe anode. Okay, so uh, this kind of structure also exists, where you have like additional electrode between the gun and the anode to focus those electron coming out from the tip of the gun. Anyway, so uh, um, this is obviously you have to have negative bias, so that you can create this crossover, or you can make them focus and create a finely thin electron beam. Now, as I said, like there are plenty of condenser lenses. The lenses uh, looks like this. Again, this is a schematic. uh, so you have mm, so this structure, and you have like copper coils. Okay, as I mentioned, this is all electromagnetic lenses, so you pass current through these copper coils. Okay, and that will create electromagnetic field. So you pass current in such a way so that it will create electromagnetic field like this, lines of force. So when the electron beam will pass through, they will basically force so that they go towards the center of the uh, center of the ACM column. Okay, so the so these lines of force basically forcing the electron beam to push them to the center. Okay, now as I said, there are several of them, these lenses, and again the whole purpose is to bring them closer to the axis, the electron beam. Otherwise, if you don't use the lenses, as the electron beam moves from top to the bottom where the sample is, they will basically diverge, right? Because they will repel each other, and they will basically diverge. So to avoid that, what you have to do, you have to come up with several lenses. Okay, uh, now although electron sizes are very small, that means you should get very high resolution out of this arrangement, right? But you see that because you see the electron will have like wave associated with it is very tiny. We did calculate the wave associated with electron, you remember, through a problem, through de Broglie's wave equation. Now the thing is this instead of achieving picometer kind of resolution, we actually get resolution of the order of few nanometer through this particular SEM arrangement. Okay, and this is because of aberration in the lenses. This is because of aberration in the lenses. What is aberration? Those who passionate about photography may know about aberration. So lens aberration is always a problem. So what it will do, so once the electron beam interact with these lines of forces of the lenses, they will basically meet at different points in the axis. So let me, if I just try to draw it once more. So say this is my lens, okay, and what happens is I have electron beam. So electron beam is incident on different parts of the lenses. Okay, so say this, right? So different parts of the lenses electron beam will incident, and what they will do, they will push back towards the axis. So this is my axis. Okay, so that's the whole purpose, right? Now the thing is, it is found that they might push back, they will push back on the axis, but that point of convergence is not same for all the ray. So some will converge here maybe, okay, some might converge here, some might converge here, because you see the lines of forces which is basically making these electromagnetic lenses will have these lines of forces will be different uh, depending on where those electron beams are interacting with them. Okay, so these lines of forces basically forcing the electrons to meet at the axis, but they might not meet at the same position. So this particular phenomena is known as aberration. This particular phenomena is known as aberration. So so meeting at different points. So this aberration will create problem, you see. So if this comes to your sample, then you don't know where to put your sample, whether to put it here, here, or here. Okay, so one way to avoid any problem is to use aperture. Okay, you remember we mentioned there are apertures. So this is condenser aperture, this is objective aperture, and so on. Okay, so there will be several lenses and several apertures, right? Aperture is nothing but a plate kind of structure where with a hole in it. Okay, so if you have a plate kind of structure with a hole in it, okay, then what it will do, it will basically block the outer beams and reduce the aberration. What I mean, let me draw it once more. So I have a lens here and I have a aperture here. So there will be an aperture, then a lens usually. Okay, so what it will do, it will basically, so it is a plate kind of a structure with a hole at the center. So what it will do, it will not allow all the beams to incident on the lens. Okay, so you see there are several beams, but it will basically remove, or it will basically prevent some of the beams to reach uh, the lens. Okay, so what will happen, this will then reduce the aberration, because you see all the beams are not interacting with the lens, only maybe beam which is closer to the center will interact with the lens. Okay, so you will end up with less aberration. If you do that, you will be able to reduce the aberration, right? So this aperture is very important. So you see there will be combination of lenses and apertures. So condenser lens, then aperture, there is another lens, then another aperture, and so on. So there is series of lenses and series of apertures. The purpose of the lens to bring those electrons closer to the axis, right? And purpose of the aperture is to reduce the amount of electron beam which is interacting with the lens. If the electron beam is diverge more, then the aperture will cancel them or prevent or block them to reach the lens, right? So that it can avoid aberration. So this is basically the combination. There are scan coils, so that you can move these, because end of the day you have to move this electron beam, right? So that you can scan your whatever structure is here, you can scan those structure, right? So you need a scan coil. So there is also scan coil in the electron beam e-beam lithography setup also, right? So scan coil is there. Now this anode will contain, as I said, it will extract electrons, it will accelerate electrons. Okay, uh, usually the accelerating voltage is of the order of few kV. So usually it is, this accelerator voltage is 1 to 30 kV, kilovolt. Okay, this is the accelerating voltage which is exist at the anode. And I said, like, there are maybe multiple anode. One anode might be used to extract electron, and other anode may be used to accelerate those electrons. Okay, if you increase this accelerating voltage, then your probe current will increase, because then the velocity of electron will increase. That means your probe current. So this is a probe, right? Electron probe. So this probe current will increase, and that will also decrease the probe diameter. Okay, because if the electron velocity is more, they will get lesser opportunity to interact with them and diverge. I hope you understand. So this, so these accelerating voltage has a very important role to play to focus the electron beam and all that. One of the thing is, if you increase the accelerating voltage, your probe current will increase, because then the electron will have higher velocity, and also it will decrease the electron beam probe diameter, because then the electrons will get lesser opportunity, okay, to interact among themselves and diverge, right? Now, but if you increase this accelerating voltage, disadvantage is, you can't, I mean, this might increase charging. Why there is charging, I will discuss it. Because electron beam is essentially, you see electron is a charged particle. So when it incident on your sample which you are studying, obviously it will create charging on the sample itself. Okay, and also can damage the sample, because there will be more penetration. Okay, if the acceleration voltage is too high, the electron will bombard on the sample, right? And it might damage your sample. Now, okay, we'll finish it bit early today, but we have some time, right? So when this electron beam interact with your specimen or with your sample, what are the signals we are going to get? Okay. So this is my sample or my substrate in which I have made or synthesized some nanostructure. So this is my incident electron or electron beam. Okay. Incident electron beam on the sample. So it will give you, so this is my specimen or sample. Okay, so it will give you different signals. For example, it will give you secondary electrons. What is that? We will discuss in a minute. So secondary electron, it will give you backscattered electron. Backscattered electron. Okay, it will give you X-ray. So these are different signals you get when the electron beam interact with your sample. You see, the whole purpose is we want to see the surface structure or surface morphology or whatever nanostructure we have made, how it looks like, whether it is nanoparticle, whether it is nanopillar, nanotube, how it is looks like. Okay, that we want to see. Now, so this electron beam, what it will do, it will interact with the sample and it will eject electron. Okay, it will eject electron from the sample. Now these ejecting electrons, okay, usually of very small energy. So this incident electron will interact with, you see there is in the sample there are lots of atoms are there. So there is nucleus, around the nucleus there are different orbitals, and in each orbital there are electrons and so on and so forth. So what it will do, it will interact with the low energy electrons, okay, and eject electrons from the sample. So this particular kind of electron is known as secondary electron. Okay, so these secondary electron, as they are of low energy, they will come out from the sample only very close to the surface. If the electron generates much deeper, they will not be able to come out from the sample. Okay, they will be reabsorbed by the sample itself. Okay, so these electrons will not come out if it is much deeper. Okay, so unless and until atoms are very close to the surface, electrons will not come out. So secondary electrons will not come out. So this kind of collision is inelastic collision, and it will give you secondary electrons. So this is the secondary electron signal. Now, if the incident energy is very high, okay, then what might happen is the electrons very close to the nucleus might come out if the incident energy of the electron is high. Now, if these electrons come out which is close to the nucleus, then electrons in higher orbitals might jump because there is a vacancy, and this will create X-ray, right? So this will create X-ray. So let me repeat it once more. So what I am saying is there are multiple interaction. One of the interaction will generate secondary electron, one of the interaction will generate X-ray, and one of the interaction will generate backscattered electron. So what is secondary electron? This incident electron will interact with atoms in the sample. Now what they will do, they will basically eject low energy electrons, okay, maybe from outer shells, and those low energy electrons will not be able to come out from the sample unless they are very close to the surface of the sample, right? So these are secondary electrons. How the X-ray will be generated? If this incident electron beam, you remember it can have 1 keV to 30 keV, okay. If the energy is too high, then what will happen? They might be able to knock out electrons very close to the nucleus. If they knock out electrons, then what will happen? It might happen that energy in the higher orbitals electron in the higher orbitals might jump and fill up that vacancy, and in the process release X-ray, okay. So this X-ray will have elemental information because this separation between these orbitals, okay, will not be same for different materials, right? So depending on their energy difference, they will generate X-ray of different wavelengths, right? So this can help you X-ray, studying X-ray can help you. So ACM do different purpose. It not only show you how this nanostructure looks like, you can also do elemental analysis. For example, you can use X-ray to find out what are the elements and in which proportion present in your nanostructure, because your nanostructure might not be make of a single element, it might have like different elements, right? So by using X-ray, okay, it is known as this particular technique known as EDAX in that ACM. It is energy dispersive analysis of X-ray. Energy dispersive analysis of X-rays. So this will give you the composition analysis, okay. What about backscattered electron? Backscattered electron is the beam electron when interact with the nucleus of the specimen atom. So it's essentially elastic collision. So it interacts and coming back, okay. It interacts with the nucleus and scattered back, okay. So this is known as backscattered electron, okay. This is essential in elastic collision. I mean, this is not, I mean, this particular scheme is not that simple. It might have like several collision. So maybe this is your incident beam. This will do like this. This might uh, go like this and so on. So what I want to mean is this backscattered electron will interact with the sample atom, and backscattered electron is nothing but the incident electron itself. Okay, so these backscattered electrons contains high energy obviously, and also very deep they can go. Okay, very deep they can go and then come back. Okay, so this might be your incident electron and this might be your backscattered electron, right? Now this and this is your incident electron. So whatever we try to discuss now is that there are three kinds of interaction. One is inelastic interaction, where secondary electron will come out. The incident electron will interact with electrons of the sample, and these secondary electrons will have low energy. So as I said repeatedly, the secondary electron will come out from the very close to the surface of the sample. Okay, X-ray will come out when this incident electron knock out electrons from the closer to the nucleus, and then some electron from higher orbitals will jump and they might release X-ray. Okay, this is good for elemental analysis. And there is backscattered electron. Backscattered electron will be the incident electron itself. It is scattered inside the sample and coming back. Okay, this is kind of a elastic collision. Now the thing is, the backscattered electron energy is higher obviously compared to secondary electrons, and this backscattered electron will also contains information of Z. Okay, so Z means the atomic number. So higher the atomic number, higher will be your backscattered electron component. Okay, higher the atomic number, higher will be the your backscattered electron proportion. Okay, sorry. So there is a thing called interaction volume. Okay, what is interaction volume? Say this is my electron beam incident on the sample. This is my electron beam. So this electron beam will interact inside the sample, and it might interact, say, this portion of the sample. Okay, and of course you can scan this electron beam to cover other areas, but this is known as interaction volume, the volume at which the electron beam interact with the sample. Okay, interaction area, as the interaction area and volume is more in case of backscattered electron and X-ray, the resolution is less. So usually the secondary electron will come very close to the surface, so maybe from this portion. So this is the secondary electrons will come out from this portion of the sample very close to the surface, whereas your backscattered electron and X-ray, okay, will come out from much deeper, because they are associated with, you remember, they are associated with higher energy. Okay, so obviously X-ray and backscattered electron resolution will be less, whereas secondary electron is coming from very small portion. Okay, so resolution from this secondary electron will be more. Okay, So if the accelerating voltage is more, beam energy is more, and then penetration is more. You see, acceleration, you remember acceleration voltage where we are applying? We are applying at the anode, right? Accelerating anode. So if the voltage is more, then the beam energy will be more, and then it will penetrate much deeper. Okay, and will give you more backscattered electron and X-ray. Now, if atomic number of Z is more in a sample, backscattered electron is more. That I have told you already. So then they look brighter, right? So backscattered electron will help you to find your Z of the sample, because there is already, say, some calibration is done already from the known sample, and if you have like some unknown sample, you can find out Z by checking, cross checking with that with a tabulation, okay, or with a calibration table. Now, detector, backscattered detector will be here, very close to the beam. Okay, backscatter detector will be here, whereas secondary electron detector is very close to the sample, because you see these secondary electrons are very low energy. So if you keep it somewhere else, those detector will not be able to capture these secondary electrons. So secondary electron detectors are very close to the sample, whereas backscattered electrons is little bit higher but very close to the axis, because these electrons are basically bouncing back. So you need backscattered electron detector very close to the axis and little bit far away, because these are high energy electron. These will be captured by the backscatter detector, whereas the secondary electron will have like low energy, so they will be very close to the sample, right? Now, how do you see the image? Okay, how do you what to show you? I mean, I can show in the net. I have some SEM image I have shown you before, but let's just Google it. So you see, these are SEM images. Okay. So see, this is SEM image. This is SEM image. Okay, so these are your nanostructure you have developed, and you can see it under the microscope. The only difference is these are optical, not optical microscope. These are electron microscope. Just give me a second. Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay, so these are different images you see. So you can, so these are different images you have made. You have synthesized the material. You see under the microscope to find out how the how these how is your nanostructure, right? Now, so this is one schematic I just found out. So you see this schematic will yeah, I don't know it is visible or not. So you see this circular purple color thing is the backscattered electron detector, whereas this orangish thing is the secondary electron detector. So secondary electron detector is much closer to the sample, whereas backscattered electron detector is away from the sample, but the thing is it is closer to the axis. Okay, and so on. So what else I want? What else can we show? Yeah, here also you see this is secondary electron detector. They haven't shown any backscattered electron detector. So these are some lenses, condenser lenses, objective lenses. These are aperture and so on, right? Okay. What else? Anything I can show you? Yeah. So the actual ACM looks like this. Okay. Actual ACM looks like this. So there is a computer where you can see the images, you can capture those images. Okay. Um, there is a column. On top of the column, there will be your electron gun. Okay. This column needs to be high vacuum, otherwise those electron will not be able to reach the sample will be back here, okay, down here. So if it is not in high vacuum, you will not, the electrons mean free path will be low and electrons will not be able to reach the sample. So it's you have to keep it in the high vacuum. Okay. And there might be several valves to isolate this column from this down portion here, because what you do, you remove this, you put your sample, but while you are removing it and put the sample, this vacuum will lost, right? But the a clever arrangement is, there is a valve to isolate this column from this rest of the down portions here. So when you open up, then this column vacuum remains intact, only the vacuum of this lower portion will go. You load your sample, you put this back, and you just only make the vacuum again for this lower sample without making the whole portion again to evacuate from here. Okay. So yeah, so this is how this ACM machine looks like. What else? So what we are discussing how we are getting those images. Sorry, I was like trying to from where I will get um, mm, okay, let me see if I want to show you a particular image. Because what I am discussing is important. So let's see, I have a particular image. Yeah. So you see, this is ACM image. Okay. ACM image will have a scale bar. Scale bar, you see, it is 1 micrometer. So from this point to this point is 1 micrometer. Okay. All this is given like 5 kV. We are applying 5 kilovolt accelerating voltage. Okay. Right. This scale is 2 micrometers, say. Right. You can go much lower than this. So this is a zoom in view of this portion. And you see here, you see these portions are brighter. These nano wires or nano protrusions are brighter. Okay. So how these images are created? So there might be brighter portion, darker portion. So if these are like nano wires, so there are dark portions also here. You see, dark portions are here and bright portions are there. So how you are creating these images? Now of these images are created depending on how much secondary electrons are coming out from the surface. Okay, say if I have a nano protrusion, so say I have this is my nanostructure. Okay, now imagine my electron beam, right? And this electron beam is scanning. Right? So you see, if we have a nano protrusion like this, or nano wire or nano rod like this, okay, more and more secondary electrons will be able to come out, because as you see, the secondary electron will be able to escape, but here the number of secondary electrons will be less. Only very close to the surface will be able to come out, but here lots of electrons are very close to the surface, you see, because this is a very tiny portion. So when you are interacting, lots of secondary electrons will be able to come out from the surface, right? So more the number of secondary electrons come out, more the portion look brighter. That is obvious, right? Because you are basically detecting those secondary electrons and creating the image. So from here, more number of secondary electrons will come out compared to this portion, right? So flat portion will give you darker impression, whereas these kind of nano protrusions, okay, or nano wire, nano rod kind of structure will give you brighter impression. So that is how from the secondary, capturing the secondary electron, you will get bright and dark portions, or in effect you will generate the image, right? So secondary electrons is independent of atomic number. It doesn't depend on atomic number. It is just depends on how many electrons coming out nearer to the surface, okay, from the surface, how many electrons are generated and coming out nearer to the surface. It doesn't depends on the atomic number, whereas backscattered electrons literally depends on the atomic number, okay. So this is known as edge effect. This particular thing is known as edge effect, because the close enough to the edge the electrons will generate, they will be close enough to the edge to escape. Once they escape, they will be collected by the secondary electron detector. Okay, but whereas when the beam is falling on the flat surface, very less amount of electrons will come out. Okay, compared to that this heel structure, right? Thus edges will appear brighter, but the flat portion will appear darker. Okay, so here we will stop today. I think I need to discuss a bit more, so we will finish the SEM tomorrow, and then we will start the another characterization equipment. Do you have any queries or questions, any doubt? No doubt. Okay, so and I will see if I get the note of SEM, I will upload it, okay, so that you can see it. And on the graphene note also, if I haven't done in the last class, I will upload it. So if you don't have any doubt, we will wrap up this session. Okay. So thank you.